today I will present the visible light as catalyzed for synthesis of molecular rings. To make you understand the reaction I will introduce, first I will give you some background knowledge for the visible lights and how it is catalyzed for the chemical reactions, and also what is the molecular rings. First, what is the visible light? Visible light is a range of the electromagnetic radiation that can be detected by the human eyes. Normally, the wavelength of the visible light is from 700 nanometer to 400 nanometers. So among the different colors of the visible lights have the different amount of energy in that. And we can see under the 500 nanometer to 400 nanometers, and this have a very high energy among the different colors of the visible lights. So lots of chemists use this part of the light to do the chemical reactions. Then when the lights meet the chemistry, we call it the photochemistry. And what is the photochemistry? Photochemistry is a bunch of the chemical concerned with chemistry concerned with the chemical effects of the lights. And then why photochemistry is very popular nowadays? Because scientists want to find a new synthesis method with under the mild and green conditions. Because in the old times, they always use very toxic compound as the catalyst, and the green condition means they can do the reaction under the safe and environmental friendly conditions, and they can convert light energies or the solar energies to the chemical energies they needed in the reactions. And there are lots of examples in daily life. For example, the photosynthesis. The photosynthesis is the plant converts carbon dioxide and water into the energy or the sugar the plant needed in the daily life with the help of the sunlight. At the same time, they will go release the oxygen, and why the photosynthesis can work under the sunlight? Because the electron in the pigment molecule can be excited by the light. And this is the free energy graph of the photosynthesis. We can see at the first, the P680, the pigment molecule, the electron in this molecule is at a very low energy level, and then they can absorb the energy from the light and reach to the high energy level, and then they will go release the energy during the reaction progress, and then they go to the next part of the photosynthesis. They will go into the P700 pigment molecule, then they can absorb the light energy again to reach another high level of the energy of the electron. Then they will give the NADPH. This is kind of like a food the plants need in the daily life. And since the electron can be excited by the light, so the molecule with that electron can also be excited by the light. Also use the photosynthesis as the example. At first, the pigment molecule is at the ground state. It's very stable. However, then the electron in the pigment molecule absorption of a photon, and the electron will jump into the higher energy level, which makes this molecule reach to the excited state. Since it goes to the excited state, it will be very active and can do a lot of the chemical reactions. The molecule can be excited by the light, so the light can drive the reactions. Use the hydrogen gas molecule as the example. The hydrogen gas molecule, with the help of the UV light, can give the two hydrogen radical intermediate. First, the UV light has a very high energy. They're going to apply these hydrogen gas molecules. Hydrogen gas molecule with a pair of the very stable electrons, and then they will go excited states, and they will separate into two radical intermediates. And this radical intermediate is very active, and they can go react with lots of the organic molecule. The UV lights have a very strong energy comparing the visible lights. However, today I will introduce the visible lights catalyze the reactions. So they need the help of the photocatalysts to help the organic molecule to absorb the light, to get the energy from the light. Before I talk about the photocatalyst, I will introduce what is the catalyst. The catalyst is a kind of the chemical compound can add into the reactions to increasing the rate of the chemical reactions. The reason why it can increase in the chemical reactions, First, we see this is the XY, substitute XY. Need to go to that high energy mountain and reach to the product. However, with this catalyst, they can find out new reaction pathways and to lower the activation energies. So this is why the reaction can increase the rate with the help of the catalyst. Then what are the photocatalysts? Why we need the photocatalyst? Because lots of the organic molecule can't absorb the visible light directly. So they need the photocatalyst to help them solve these problems. And there are two types of the photocatalysts used in the reaction. First is transmetal complex. Transmetal complex is a kind of very traditional photocatalyst, and this is discovered in several years. This is the Resinian complex, and this is used in the lots of the photochemical reactions, and it can absorb the light directly and transfer the light to the substitute. And also, they have the metal-free compound as the photocatalyst. Since there is no metal in this photocatalyst, so this reaction can work under the much greener and mild ways. And this is the bio-inspired photocatalyst. And there are three functions for the photocatalyst. First, it can attach to the substitute to get the intermediate and this intermediate can absorb the visible light. For example, we can see this graph, the UV vis absorption graphs. With the help of the photocatalyst and the substitute attached together, they get a sub-photocatalyzed complex. And this complex at 400 nanometer, they can reach a very high absorption comparing with just the substitute or the photocatalyst. And also, it can do the energy transfer. The energy transfer is a photocatalyst can gain the energy from the lights, and then they can transfer the energy they get from the lights and into the substitute, and makes this carbon-carbon double bond go to excited states and give the radical intermediate. Then it can easily react with another double bond and form a rings. And the last, they can do the electron transfer. The electron transfer is the photocatalyst can transfer electron to do the oxidation or reduction reactions. This is a reductive cycle for the photocatalyst. The photocatalyst was excited by the HV photon at the 450 nanometer, which is the wavelength of the blue light, and then they will get the electron from the substitute D, and then they will give the electron what they get and give back to the substitute A, and they can finish this cycle. After I introduce the photocatalyst and visible lights, and what they can do in the chemical reaction, they can synthesize a lot of kind of the molecule rings. And there are two types of the molecule rings. One is a homocyclic compound, and another is a heterocyclic compound. The homocyclic compound is a ring structure, contains only the carbon atoms. And there are many types of the homocyclic compound. The first is cyclopropene, the 3-membered rings, and cyclobutene, 4-membered rings, cyclopentene, 5-membered rings, and cyclohexene, the 6-membered rings. Today, I will introduce the cyclobutenes. Cyclobutene is the 4-membered rings, and there is the 1GF, IGF-1R inhibitor contains a 4-membered ring here, and this is the anti-cancer drugs. And comparing with the 6-membered rings and 5-membered rings, 4-membered rings has a smaller size, so it is very active and rapidly open and rapidly form. And so this is always used to design and preparation of biological active compounds. And to synthesize the 4-membered rings, we always use the 2+2 cycloaddition reactions. And this reaction is very easy to understand. We have the two carbon-carbon double bond, and one of this bond will to form this carbon-carbon bond, and another they will go from this one that goes through like this way, and they can form the new bond. The red is the new one. And use the visible lights, we can do the intermolecule 2+2 photocyclidation reaction. Intermolecule means the reaction between two different molecules. This is we can find the one double bond here and another double bond in this alkene, and then they can do the 2+2 cyclidation reaction to form the 4-membered ring here. With the help of the transmetal complex, this big stuff is the photocatalyzed. They use in the reaction, and this reaction can under the room temperature and the blue lights. So this reaction is very easy to operate, and this reaction gives the 99% yield of the product and very high sterol selectivity. So this reaction has a very high efficiency. The reason why I want to introduce this reaction, because this reaction has a larger of improvement than the previous reactions. This reaction is discovered by Young's group in 2016. They needed two catalyzers to form the 4-membered rings. One is the photocatalyzed, it can absorb the visible lights, and then they do the transfer the energy. And however, the substitute need a very high energy to reach the excited state, so they should connect to the Scandian complex to lower its excited state, to lower the energy they needed for the excited states, so they can get enough energy and reach to the excited states. So the double bond also here react with the alkene and form the 4-membered rings. And this is what reaction I introduced before, and this is discovered in 2017. And this reaction only needed one catalyst, and also they have the wild substitutes group than the previous reactions. The reason why this reaction can work under the visible light, we can do the UV-based absorption technology for the intermediate. And this is the intermediate when the substitute and photocatalysts combine together under the 400 nanometer. They reach to very high absorption comparing with the dashed line. The dashed line is only the substitute, and the green line is the photocatalyzed. So that means when they combine together, they have the ability to absorb of the visible light and to get the energy from the lights and do the following reactions. To understand one reaction deeply, we need to understand the mechanisms of this reaction. First, the radium complex, which is the photocatalyst we use in these reactions, will connect to the nitrogen and the ketone. And after excited by the visible lights, it can go to the excited singlet states, and then after intersystem crossing, it will go to the excited triplet states, and then we can see I have the two radicals, and this carbon can go react with the alkene and to form the carbon compound here. And then we have the two radicals. This is too close. This is the 4-membered rings, and we formed another carbon compound here after intersystem crossing. And last, they will break up these two bonds and release the product. And the rest of the photocatalyst will go into the next catalytical cycle. Since what I talked before, this reaction has a very wild substitute group, so this can make a lot of the product. This is the parts of the product this reaction can make. And one thing is very interesting is the 3Y. 3Y is the estrone. Estrone is a minor female sex hormone. And the 4-membered rings here is very easy to open. So I think with this is the estrone structure. When the 4-membered rings open up, and they can react with other organic molecule and to form the medicine with the estrone structure. And the next 2+2 reaction I will introduce is the Intramolecule 2+2 Photocyclidation reaction. The intramolecule means the reaction between the one molecule. There are 3 ways to make these reactions. We can say the double bond here, they can form the 4-membered rings with another double bond within this molecule. The first is they can use the UV lights. The UV lights have very high energy, so it can directly excite the double bond and to give the radical intermediate, and then react with another carbon-carbon double bond. And another way is they can use the visible lights and the photocatalyzed. The photocatalyzer used in here is the transmetal complex. This is very traditional photocatalyzer I mentioned before, so it can transfer the energy to the double bond and then go react with another double bond. And this is the very new method found in the recent year, and this is the bio-inspired photosynthesis, photocatalyzed, and this is metal-free. So with this photocatalyzed, the reaction can work under the green and mild condition, and also without the metal can make the reaction works cheaper than, and this photocatalyzed is cheaper than the transmetal photocatalyzed. And this reaction also have a wild substitute group. The X can be oxygen or the carbon or the nitrogen groups. And however, comparing with the previous 2+2 reaction, this reaction have the lower stereoselectivities. The reason why this photocatalyzed can active by the visible lights. This is the photocatalyzed used in the reactions. This is the filming. The filming can, under the 400 nanometer, the wavelength of the blue light is reached to the high absorption here. So it can absorb the visible lights and transfer the energy to the substitute. What I talked before, this reaction, it has the lower stereoselectivity. So there are two products for this reaction. One is the minor product, another is the major product. The major product always the cis product. The cis product means these two groups is going to in the same way, and the minor product means one group is go forward and another is trans product is the minor product. And trans product means that one is go forward and another go backward for these two groups. And the mechanisms of this reaction is very simple. First, the photocatalyst can get the energy from the visible light. The two is the photocatalyst reach to the excited state. Then they do the energy transfer. They can transfer to this carbon-carbon double bond and reach to the excited state and give the radical intermediate. And then they can react with another double bond and form the four-membered ring here. And there are also a lot of applications for this reaction. One is very interesting is this is applied for the quaternary ammonia. This is the spiral quaternary ammonia. This double bond combine together do the 2+2 cyclidation to form the four-membered ring here. And this is another can do the 2+2 cyclidation do the four-membered ring here. And this ammonia is always used as the catalyst for the asymmetric phase transfer reactions. So this is very useful for the chemical studies and the biological studies. After I introduce the homocylic compound, I will introduce the next part of the molecule rings is the heterocylic compound. The heterocylic compound is also the ring structure, contains at least two different elements, always the nitrogen items or the oxygen items. So there are also many types of the heterocylic compound. And today I will introduce the ferro first, this one. And ferro is a 5-membered rings with the nitrogen items. And this is the structure of the ferro. And ferro is very important in nature products and medicine studies. So they are involved in lots of the drugs or the nature products. For example, this is the bilirubin. Bilirubin is contained in the human body, and the level of the bilirubin can indicate a certain distance. And this is the one ferro ring here, and this is another one. And the next is the vitamin B12. There is a planar structure in vitamin B12, and they contain four ferro rings. One here, and the next one, and this is the third one, and the fourth one. And these four rings can combine together, give the planar structure for the B12. Vitamin B12 is a cofactor in DNA synthesis, and fatty acid metabolisms and amino acid metabolisms. We can use the 3+2 cycloaddition reaction to form the 4-membered rings with the nitrogen atoms. And this is the 3+2 cycloaddition reactions. We use this big stuff is the metal-free compound as the photocatalyst under the room temperature and the blue lights. First, we need to open the nitrogen heterocyclic rings. This is 3-membered rings, so this has a very small size and very easy to open with the help of the photocatalyst and the visible lights. And then, after the ring open, they can react with the triple bond, and they can form the furan rings in the product. This gives the 70% yield of the product. So this is pretty high yield, and the mechanisms of this reaction is first they need to do the open rings. This picture is a little bit small, and I will zoom in and to see the details for the ring opening process. First, nitrogen with a pair of the electron, they will do the oxidation reaction first, and the nitrogen with a positive charge with a single electron, and this single electron can do the electron push and open the ring, and to give the intermediate B. And this intermediate B has the electron isomer. This is the B's electron isomer, and then they can do the radical addition with the carbon-carbon triple bond, and then they can form the bond here and give the intermediate C, and we can see the radical here, and then we can add the electron into this radical and have the negative charge and the positive charge here and negative charge easily to make the carbon-carbon bond to close these 5-membered rings. And the photocatalyst in these mechanisms used to do the electron transfer. It helps the substitute to do the oxidation and reduction reactions and form the rings. And the application part for this reaction, they can give the HMG-CoA inhibitor. HMG-CoA inhibitor is this big stuff, and first they use the nitrogen heterocyclic rings, and then use the 3+2 cycloaddition, give the furan ring here, and then they can follow total synthesis progress and give the HMG-CoA inhibitor. I will not go into more details about the total synthesis part. If you are interested, I quoted the paper here, and you can read the paper. And the HMG-CoA inhibitor is a limited enzyme, and it has low in and total low density lipoprotein collaborisms in animal models and mice. And the next heterocyclic compound I will introduce is the Oxidor. Oxidor is the 5-membered rings contains nitrogen and oxygen atoms, and this is the structure of the Oxidor. Oxidor also involved in the lots kind of nature products and medicines. For example, the telomeres. Telomeres have a lot of the oxygen in here. For example, they have one here and another one, and this is used to protect the DNA strands physically. We can see this yellow dot here. This is the telomeres, and they also use the 3+2 cycloaddition reaction to form these rings with the similar mechanisms. First, they go to open the 3-membered rings, then they go react with the ketone, and also they need the photocatalyst in this reaction. This is the photocatalyst they use, and under the blue lights and the room temperature, and this reaction gives the 80% yield of the products. Since this reaction has the similar mechanisms of the previous reaction, I will not go into the detail for the mechanisms, just jump to the application part. This synthesis method can give the COX-2 inhibitor. They will react this part and go react with the oxygen, and then they can give the COX-2 inhibitor. COX-2 inhibitor is an enzyme response for the inflammation and pains. So this is used into the pain relief medicine, which is NSAID, and this is always in our daily life. And the last heterocyclic compound I will introduce is the isoxazolams. Isoxazolams is the 5-member rings, also contains the nitrogen and the oxygen, and this is very new 5-member rings. So there is only a few products and drugs in this contains this structure. For example, the fluorliner, we can see the ring this contains in here, and this is the prostacyclopentacin medicine. So this is involved in the lots of the PET medicines. And we can also use the 3+2-cyclidation reaction with the similar photocatalyzed and mechanisms to form these rings. First, they also need to open the rings with the help of the blue lights and the photocatalyzed. And they have the nitrogen-carbon double bond, and then they will go reaction with the carbon-carbon triple bond to do the 3+2-cyclidation, and they can form the isoxazolams. And this reaction up to the 90% yield. And interestingly, this 3 reaction can only work with this photocatalyzed. The research group tried to replace the photocatalyzed with the transmetal complex, the ricinium complex, what I talked before, the very traditional photocatalyzed. But the reaction can't work or give very low yield of the product. Since there are a few natural products and medicine contains this structure, so I will jump the application part and talk about the efficiency of this method. They do the gram scale reactions. The gram scale reaction means they put a large amount of the substitute and do the reaction. They put 1.0 grams of the substitute, and then they give the 70% yield of the product. So this is not a very low yield, and it is a very good yield. So the industries and factories can consider use this synthesis method to get a large amount of the product with the isoxazolam structures. And in summary, there are 3 characteristics of the visible light catalyzed reactions. First, they always use the blue lights, because among the different color of the lights, blue lights always have a very high energy. So, and also they need the photocatalyzed. They need the photocatalyzed to help the organic which cannot absorb the visible light directly and get the energy from the visible light. And usually it have the very high absorption under the wavelength of the visible light. Also, they have involved the radical intermediate during the mechanisms of the reaction. And this radical intermediate always excited by the visible light with the help of the photocatalyzed. And that's it. Thank you.
Questions?
So you talked about some 2+2-cyclidations.
Yeah.
And you said that under these conditions, we should think about them as triplet biradicals, with the radicals pointing in the same direction, right? You could also imagine a case where you didn't go through a singlet; they were still, or you went through a singlet diradical instead. So you've got unpaired electrons, but with spin opposite instead of spin parallel. Did they talk about how do you tell the difference between one or another, or how you get one versus the other?
I think they do not mention so much of the spin in their paper.
So the slide with their intersystem crossings and such.
Yeah.
Right? In some cases, that's not required. You can just react from the single.
Yeah.
Okay.
So it appeared that there were several different types of solvents that these different reactions were using from acetonitrile. I think there was a there's a DC something, which that thing, dichloromethane. So how much does the solvent affect that primary absorption around the 400 wavelength for the blue LEDs?
The interesting stuff is I do not mention is this solvent they use is CH3CN, and for the previous another two reaction they use DCE, and they do not mention so much about the solvent influencing how they can absorb the lights. They just give like a table about the test results of the solvent.
So before this, you talked about oxazole chemistry, the 3+2 there.
Yeah.
That started from the three-membered ring, right?
Yeah.
Aziridine, is that right?
Yeah,
Right.
this one?
Yes.
This one.
Not aziridine. It's
Yeah.
Yeah. So, how should we think about this, right? Is this does the three-membered ring open up
Yeah.
first
Yes.
to get what?
The three-membered ring open up, and then they can get. I think they can get the triple bond, the nitrogen triple bond.
Could you draw it with the marker ring?
Yeah. Now they do the similar process, they will become the positive charge here. This is kind of what I think we can. Yeah.
So why don't we draw the arrow the other way, and then you can get a. You could draw from the nitrogen going to the left instead of the right.
Yeah.
And then you end up with a C minus on the right.
Yeah. So yeah, that should draw like this way.
It's close, but you want a minus sign between the nitrogen and the phenyl on the right. Yes, there. Yeah. So plus there, and then minus on the right.
This one?
Nope. Nope, the other one. CH2? Yeah, right. Minus sign there. Okay. So the ring opens first, and then it adds to the
ketone.
the aldehyde. Okay. Okay.
It's kind of fun to see how useful the blue LEDs are, given that was the Nobel Prize, what was that, 2, 3, 4 years ago, I think? Are there other experiments or other lower energy photocatalyst reactions that can occur, or is it only really the blue LEDs with the higher energy?
The most visible lights catalyze the reaction. I read in paper they always use blue lights. The longest wavelength I find is 500 millimeters, but I think this is also in the blue lights. Yeah.
I saw in some of the reactions that they let it go for 30 hours. Is there an efficiency factor built in? Like, is that the only way they're getting their yields by running it for 30 hours?
Which reaction is?
Just scroll back here.
Yeah.
The gram scale reaction at the end.
Oh, gram scale reaction. This reaction. Yeah, because I think this has a large amount of the substitute. So I think this reaction should work on the longer time than the normal the 3+2 reactions. And they do not mention so much about the certain hundreds hours and give the 70% yield. And they just to say they modified some of the reaction conditions, and then they give the this product with 70% yield.
When you see long times in reaction builds, sometimes it's intentional and sometimes it's because that's when you get to it. But when you see 16 hours, that is usually, we'll let it go overnight. But 30 hours is a little more intentional, yes.
I could also be, I forgot.
Yeah.
Well, I'm just, because you made a comment that some of the, like, for this reaction in particular, 70%, that's pretty good for industrial scale.
Yeah.
That's also 30 hours.
Yeah.
it's got to run, and converting it from a hot synthesis to a flow synthesis is not, as Seth would say, non-trivial.
Non-trivial. But that's where you want to go. Yeah.
Other questions? All right, let's thank the speaker. 12 minutes.